Hi everyone, my name is Sujin Bae, Associate Manager at CIRAM. Today I'll be talking about the theme, the fusion of knowledge graphs and social network analysis. These days, so many kinds of text data are being generated in real time across different fields. What I'd like to show you today is how we can turn that text into meaningful graph structures and then apply them within social network analysis. If you stay with me until the end, you'll not only get a clear picture of the concepts, but also see real research cases and a live demo. So please sit back and enjoy. Let me give you a quick overview of today's session. First, in session 1, we'll start with a brief introduction. In session 2, we'll explore how text can be transformed into networks. And finally, in session 3, we'll look at case studies to see these ideas in action. First, shall we take a look at one of today's key topics, the knowledge graph. Some of you may already be familiar with the term knowledge graph, while for others it may be new. A knowledge graph is a graph-structured data model that represents real-world entities and their relationships with semantic meaning. For example, as you can see in the illustration, various types of real-world entities such as people, artworks, and places are represented, and the relationships among them are connected in graph form. Facts like the Mona Lisa is housed in the Louvre, Da Vinci painted the Mona Lisa, Lily is interested in Da Vinci, and James is Lily's friend are expressed as entities and their meaningful ties. A knowledge graph captures the relationships among different types of entities, as well as multiple layers of relationships between the same entities. For instance, A and B might be friends, colleagues, and also have a financial relationship at the same time. Now, if you've already known social network analysis, you might be wondering, how is this different from social network analysis? So today, I want to talk about 3 ideas that are similar but also a bit different: social network analysis, ontology, and knowledge graphs. A social network is basically a simple model of social interactions. It just shows who's connected to whom, usually between the same kind of actors, like person to person or organization to organization. Ontology takes a step further. It clearly and formally defines the important concepts and their relationships in a specific domain. For example, in politics, you might have people, parties, policies, and states. The rules are set in advance, like a person belongs to a party, a person proposes a policy, or a party governs a state. But if you flip it around and say a policy proposes a person, that's just wrong. Because it gives meaning and rules, it also lets you reason out new connections. If A belongs to Party X and Party X governs State Y, then you can infer that A is part of the governing party of State Y. A knowledge graph is similar to ontology, but much more flexible. It usually expresses relationships as triples: subject, predicate, object. What counts as an entity or a relation can change depending on context. It pulls together data from many sources and focuses on what the relationships actually mean. Ontology is strict to keep things consistent, while a knowledge graph is more about using those semantic connections for practical stuff like query, search, and recommendation. And the trend now is that these 3 areas are starting to overlap and borrow from each other. Social network analysis is bringing in text and semantic ties for things like discourse or communication studies, and knowledge graphs are often built right on top of ontologies. We just went over the basic ideas of social network analysis, ontology, and knowledge graphs. As I mentioned, all 3 share the common ground of structuring entities and relationships from different sources. But for today, I'd like to focus on one question in particular. How can we turn text data into networks? And what kind of meaning does each approach bring? Here, I'll introduce 2 main ways of turning text into networks. One is the co-occurrence network, and the other is the knowledge graph. Let's start with the co-occurrence network. This approach takes words from a text and defines relationships based on whether those words appear together in the same sentence, paragraph, or context. On the left, you see the Wikipedia page for social network analysis, and on the right, you see the keywords extracted from that page visualized as a network. In other words, while the document itself may look like plain description,
once you map the keyword relations into a network, you can instantly see which concepts are central and how different topics are connected. By structuring text this way, you go beyond just summarizing content. You can actually uncover the hidden structures and patterns within. How about knowledge graphs? The text you see on the screen is part of the synopsis of the movie Avengers. In a knowledge graph, we don't use every single word, but instead pull out the main entities that interact or form meaningful relationships. In other words, we identify what is connected to whom and in what way. Then, by referring to the relationships described in the text, we define the links between those entities. On the right, you can see the result, the extracted entities and their connections visualized as a knowledge graph. So let's compare these two approaches. On the left is a co-occurrence network built from social media posts about abortion. Here, the links are based on how often word pairs appear together in the same sentence, paragraph, or context. As you can see, this works well for quickly spotting core topics for keywords, but it tends to include noise, and since direction and meaning aren't captured, it's not well suited for interpreting things like cause and effect. On the right, we have a knowledge graph, and this one comes from a news story where former President Trump urged Coca-Cola to use sugar instead of corn syrup. The graph shows different types of entities: Trump, the Coca-Cola CEO, the U.S. government, Coca-Cola, and their relations are clearly defined, like requested, interviewed, used. With this structure, you can do much deeper analysis and explore the relationships more precisely. But, of course, building it is more costly and depends heavily on data quality. In the end, these two methods serve different purposes rather than one being better. Co-occurrence networks are strong for quick exploration and trend spotting, while knowledge graphs are powerful for detailed relationship analysis and understanding story flows. When did researchers first start trying to build networks directly from text? Actually, this idea has been around for quite a while. Here's a paper from 2013 by Professor Campbell at MIT Lincoln Lab. The study showed that you could automatically build networks from unstructured data like news, social media, and even sensors by extracting entities and their relationships. The challenge back then was that it required a mix of complicated tools like NLP pipelines, entity recognition, rule-based systems, and each piece had to be implemented separately, which made it hard to apply in real research. But now things have changed. With LLMs or large language models, this process has become much more accessible. Today, you can take news articles, research papers, reports, even social media posts, and identify entities and extract relationships to build a knowledge graph. Of course, LLMs aren't perfect, they can be inconsistent, and the results still depend a lot on careful prompt design and domain-specific post-processing. Without that, the quality isn't quite there yet. Still, using LLMs to build networks from text is especially valuable when direct relationship data is hard to get. Take North Korea's power structure, for example. Since official data is scarce, you can piece together a picture of the network using clues from news reports or policy documents. And most importantly, because knowledge graphs are based on explicit relationships rather than just keyword links, they're a much better fit for applying social network analysis methods to real-world phenomena.
So then, what about real-world cases? How have people actually built or analyzed knowledge graphs from text in practice? The first case comes from digital humanities, especially in the study of classical texts. This research pointed out that traditional historical studies relied heavily on the slow qualitative analysis. But with the rise of large language models, or LLMs, it's now possible to automate much of that process and bring in quantitative methods. So in this study, they use LLMs to extract personal names and place names from the Han Dynasty text Yan Ti Lun. Then, based on how figures were mentioned together, they built a knowledge graph. On the right, you can see the visualization of the result. In the graph, Confucius appears as a central node, reflecting his role as the core of Confucian thought, while Chunxi Huang and Shang Yang stand out as representatives of legalist thought, positioned in contrast to Confucius. What's interesting is that this graph not only reveals the archaeological conflict between Confucianism and legalism, but also shows how some figures drew on arguments from both sides, making visible a kind of intellectual fusion. The second case from politics and public administration. This study proposed a way to automatically extract political networks, specifically networks of members of parliament, from text. The research had two main steps. First, they use LLMs on political news articles to identify MPs, capture the context of their relationships, and even extract sentiment, positive or negative, between them. With that information, they built a knowledge graph of MPs. On the right, you can see the resulting network. The colors show the sentiment, while the labels on the links describe the type of relationship. Next, they brought in data on MPs' legislative activity, such as whether they belong to the same party, share the same district, or appear together in news with certain sentiments. They also measured network distance, how structurally close two MPs are in the graph. Then they ran regression analysis to test how each of these factors influenced legislative agreement, meaning whether MPs voted the same way on bills. The results showed that relationships and sentiment captured from text do correlate with legislative agreement. In other words, the political ties that appear in the news don't just stay in the news, they reflect real alliances and influence in legislative behavior. So to sum up, this study demonstrates how LLMs can be used to extract political networks from text and then validate them against actual social behavior, showing strong potential for studying political power structures and even informal networks in the future. Next case, which combines discourse analysis with organizational dynamics. In this study, the researchers extracted relationships from in-depth interviews. The goal was to see how organizational ties are influenced by shared discourse. To do this, they first analyzed documents published by militant groups in Afghanistan and identified key topics. Then, using interview data, they mapped the ties between militants, such as colleagues, friends, or hierarchical relations. On the right, you can see the 4 multi-layered networks it constructed. They then analyzed how sharing discourse affects the formation of ties using SAOM, the stochastic actor-oriented model, which simulates how ties change over time based on actors' decisions. The main finding was that sharing cultural elements, essentially discourse, plays an important role in building positive ties between militants. This effect was especially strong when militants were on the same level of power. On the graph to the right, you can see that the more discourse militants shared, the higher the probability of forming comrade relationships. So this study shows how combining content analysis with social network analysis makes it possible to explain both context and organizational structure together. This is the last example. Knowledge graphs were applied to supply chain resilience in this study. This isn't text-based, but is closer to an ontology-driven approach. Typically, big companies know their first-tier suppliers fairly well, but information becomes scarce when you move down to second- or third-tier partners, or even to raw materials. That lack of visibility makes it hard to predict risks or respond effectively in times of crisis. To address this, the study integrated Simon's internal data, such as first-tier suppliers, business scope, and material usage, with public data on raw materials and countries. From this, they built a knowledge graph with 8 entity types, including suppliers, parts, raw materials, and countries, and 11 relation types, such as supplies, too. On the right, you can see the schema they designed. They then analyzed the network of supply relationships, focusing on centrality to pinpoint critical connectors and potential risks. In total, they identified
988 key suppliers and were able to show what kinds of risks would emerge if those suppliers were removed from the chain. By structuring the entire supply chain as a knowledge graph, the study provided a practical decision-making tool that helps organizations respond to crises and strengthen resilience, making it a standout example of applied knowledge graph analysis. So far, we've covered the concepts, the approaches, and some research cases. Now let's take a look at how we can actually build social relationships from text in a simple way, using a tool.
What you see on the screen now is NetMiner, our network analysis tool developed in-house. Recently, we released a macOS version. Personally, I am very pleased that I can now run NetMiner on my own MacBook, and today's demonstration is prepared in this macOS environment. Today's demo uses recent news data. Based on reports that Germany, France, and the United Kingdom will soon begin procedures to restore UN sanctions on Iran, I will first show the difference between a co-occurrence network and a knowledge graph, then run basic analyses and visualization on the resulting networks. First, we need to import the text data. Use File, Import to load a data file. If you have used NetMiner before, you may notice the menu structure has changed. Instead of separate menus by data format, it is now organized into two types. Structured data refers to spreadsheet-like formats with fixed rows and columns. You can import CSV or Excel here. Unstructured data is used to bring in plain TXT files without predefined structure. Select the prepared article, assign a name, and import it. Opening the item shows the file path along with the full article text. With this data, we first build a co-occurrence network. In Pre-Process, Text, choose Word Network. There are two main ways to generate co-occurrence. The co-occurrence method creates relations among all keywords that appear together within a document, while the sliding window method links only nearby words. Select the news item as the data source and specify the text column to analyze. In Main Process, set the language. English and Korean are supported, and Chinese is in preparation. For English, if you disable case handling, the text is lowercased for analysis. To keep things simple here, I will disable case handling and run it. After processing, the word network lists the extracted keywords. Each row represents a relation in which two different keywords appeared together. The final column is the weight, indicating how frequently the pair co-occurred. To use this in analysis or visualization, add it to the dataset. Go to Visualization, Network, select the network, and apply a default layout for a quick placement. Other layouts can reveal community structure more clearly, and you can choose according to preference. Even without further analysis, the visualization lets you intuit which keywords sit at the center. For example, Iran, being central to the story, has many connections and occupies a globally important position. A term like snapback may not have many direct links, but can sit at a bridge between larger groups, so it is likely to score high in betweenness centrality.
A co-occurrence network is useful for quickly grasping the main content, but when you want a simpler view of the key entities in the news, a knowledge graph is convenient. The knowledge graph feature is currently offered as a lab function and uses an LLM, so you must register an API key in advance. The AI assistant that helps interpret results is also included. Once a key is registered, you can use the AI features easily. Supported services include ChatGPT and Gemini, as well as Llama models that can run locally without an API key. Gemini offers free models, so it is recommended in many cases. You can find API key issuance instructions in the Help section of the manual, and you may contact us if needed. To run the knowledge graph, select the data item and the column containing text and execute. Running it directly leaves identification of key entities and their relations entirely to the LLM. If you enable extraction options, you can impose simple rules that restrict scope. For example, you can request only persons or persons and organizations. Here, I select persons and organizations and run it. The LLM then extracts entities and relations according to the rule. Omitting rules can be a bit faster, but choose based on your needs. In the overview of results, you see the number of extracted entities. Here, the entity types are 2 because we limited them to persons and organizations. The total number of relations and the number of relation types are also reported, and various relation labels are extracted based on context. In the Nodes tab, you can review the major entities organized by organizations and persons. In the Edges tab, relations between entities appear as rows reflecting context from the text. You can also add these to a dataset and use any function that accepts a network as an input. To quantify key actors or entities, apply centrality analysis. This reveals which entities are important within the network, and organizing the results makes the prominent ones clear. You can also add these results to the dataset for other analyses. To find subgroups, run community detection. Several methods exist. The Levine method is fast and accurate. Between the spaced community detection measures the betweenness of links and removes high betweenness links one by one to form communities, which is useful for examining how the network splits step by step. Here we will incorporate direction and weights and run it. When analysis finishes, you obtain multi-stage community results. As links are removed and the network splits, a new result is recorded at each stage. The process continues until all the nodes are fully separated. The results are given as membership numbers, indicating which community each node belongs to. Each stage can also be added to the dataset and be used as node attributes. I will visualize a set of results by adjusting options. You can tweak node spacing and repulsive horses to improve readability. In the visualization, map community results to colors
and map centrality to node size so that important entities appear larger. This makes it possible to see at a glance which entities are central in the news dataset and which ones play important roles, and to summarize which entities cluster together by color. In the example, the light blue group corresponds to European countries, showing their responses and various relations with Iran. Nuclear-related organizations form another cluster. In sum, with a single text source, you can perform both content analysis and social relation analysis. Although text varies by field, this approach can be tried easily across domains. As the demonstration shows, you can import text and apply several analyses to obtain meaningful results. Although not shown today, you can also use the extracted network structure to predict or classify node attributes. These are graph neural network models. For instance, if you build a stakeholder network from news on a specific issue and add stance or orientation labels to entities for training, then when a new article introduces a new actor whose stance is unknown, you can infer that stance based on what was learned earlier. We planned this separate webinar on using graph structures for prediction. Today, I introduced how to use knowledge graphs and social network analysis along with real research cases. What used to be difficult has become accessible thanks to LLMs and other technologies. We provide tools that make social network analysis easier, and when researchers' ideas are added, even more interesting results emerge. If you need any support as you try these methods, feel free to contact us.